The title is Investigation of Structural and Optical Properties of Nanocrystalline Zinc Oxide. And the procedure is as following. He will make his presentation, and then there will be questions from the opponent. Welcome, Mr. Buter. And then there will be questions from the audience. And finally, I have to decide if he deserves or not. Okay, let's start.
Thank you so much for your coming. The title has Mr. Cole, the investigation of structural and optical properties of nanocrystalline zinc oxide. The basic thing, why I was interested in the zinc oxide, because they have a large prospective property, having a wide band gap, near about 3.3 electron volt. Band gap engineering, the most important property related to the zinc oxide, by doping or by composition of magnesium, barium and cadmium. With the modulation of magnesium to related to the zinc oxide, they are used in optoelectronics property. Actually, zinc oxide is a verticed structure, while the magnesium is a cubic, but with the doping or with the composition of 40%, zinc oxide remains verticed, but when the composition increased up to the 60%, then the zinc oxide changed verticed into cubic, and their band gap increased dramatically. And that's why they are used in ultraviolet lasing property. They have a high exciton binding energy, near about 60 milli-electron volt at room temperature, and bi-exciton value is 15 milli-electron volt. Zinc oxide is a transparent material. Their transparency is greater than 93%. And the wavelength range is 400 to 500 nanometers. Zinc oxide exhibits the ferromagnetics property. The ferromagnetics property are diluted magnetics semiconductor. These semiconductors are useful in spintronics property, I mean spin plus electronics. With the increase of carrier charges, we can enhance the involvement of the spin and then can use the useful property for the n-type doping. Zinc oxide is a non-symmetric material. Therefore, excess of zinc is present. Therefore, zinc oxide is considered as a n-type material. For group 3, gallium, indium, aluminum, they substitute as a zinc place, while chlorine, iridium, group 7, they substitute as a oxygen. But the most important is used for n-type is a hydrogen, because they, due to the doping in the hydrogen, they shows a n-type because his ionization energy is 13 milli-electron volt. To get the p-type doping, wide direct band gap, is a very difficult task, because p-type doping, especially NP, nitrogen, potassium, arsenic and antimony, they are still controversy, because although nitrogen is considered as a p-type doping in the zinc oxide, but the problem is that nitrogen is not soluble in zinc oxide. Although we use by ion implementation, we can solve the zinc oxide on a nitrogen. There is a many areas of application related to the zinc oxide due to the transparent and flexible electronics, spintronics, nanotechnology, especially nanorods, nanowires, and nanonails. For the optoelectronics, they are used in ultraviolet, blue, light emitting diode, light diode based zinc oxide. But the basic task is a structural and optical properties are great importance related to the zinc oxide. Zinc oxide is considered a luminous material. For the recombination, there's a non-radiative emission and radiative emission. For non-radiative emission, point defect, dislocation, surface and interface state. While the radiative emission, they possess near band edge emission and deep level emission. Near band edge emission is also called ultraviolet emission. In ultraviolet emission, they possess the electronics emission or exciton. At low temperature, near band edge emission is very difficult because the radiative emission is the efficiency of the radiative emission is very low. That is 10 raised to power minus 1 to 10 raised to power minus 3. Although deep level emission, there is a still controversy. Maybe due to some defect or impurity which are present in the zinc oxide. And thus the deep level emission is a defect emission. The near band emission, its range is up to 375 to 400, this range. But the deep level emission is this range. They emit green, yellow and orange emission. Highly demand is to obtain ultraviolet emission in zinc oxide, especially for light emitting diode. What was our aim, or which motivate us to do this work? Here, first thing, zinc oxide was grown on a silicon. Why we used a silicon? Because silicon is a good electrical and thermal property. It is a cheaper and easily available in the market. There is many other substrate which has a small lattice mismatch, but they have a high cost and not available in the market. But the problem is that to grow the zinc oxide, that is a tough task because silicon has a oxidizing material, and without using a buffer layer on it, direct growth on a silicon was a tough task. And we want to grow the zinc oxide on a silicon at a low temperature to get a good prospective property. The second thing, after getting a good result on a silicon, we got an idea. If we will make a homoepitaxy template and then again grow on a zinc oxide on it, due to the homoepitaxy, how much growth they will become 2-dimensional or 3-dimensional. We want to check this thing. The third thing, during the growth of zinc oxide or any growth technique, control of oxygen pressure in the chamber, that is a difficult task. Actually, they affect the structural and optical properties. We want to check how much affect whether oxygen is rich or oxygen is poor. The fourth important thing to grow the zinc oxide on a silicon substrate. Actually, silicon and zinc oxide, they have a very close lattice mismatch, and we grow the N-type zinc oxide on a P-type silicon carbide. N-type zinc oxide on a P-type silicon, so that we will reach PN junction for light emitting diode. Although the work was very small, but we only analyzed the structural and optical property, how much they affect on it. Here, what was the growth? How they grow? Actually, that a quartz tube is enclosed in a furnace. Furnace is attached with different electrical lines. Here, a 3 temperature region, T1, T2 and T3. In T1, zinc compound is placed on a zinc board. T2, though 2 gaseous inlet are enclosed inside it. While in T3, chemical reactions are going inside it. When the furnace is increased, when the temperature is increased, this quartz tube reaction is going on it. Zinc compound evaporate due to the excess of argon gas and nitrogen for little bit. And here we flow oxygen we use as a precursor. Due to the zinc acetone and oxygen precursors, chemical reaction take place, and all the zinc oxide are deposited on the substrate, which is a perpendicular on this place. Here the temperature is variable. We can change the temperature of this region. For different sample, we change the temperature for different place. What was the result? We divided our result in a 4 sections. First, zinc oxide grown on a silicon, different at temperature, keeping oxygen as a rich. The second thing, zinc oxide was grown in a homoepitaxy template. The third thing, we discuss the zinc oxide grown on a sapphire substrate. Here we make a condition. In some sample oxygen is rich, in some sample oxygen is poor. The third thing, that is the most interesting, that zinc oxide, N-type zinc oxide is grown on P-type silicon carbide. Here all are these samples and their technological parameter, growth of technological parameter are given. What was the structural effect when the zinc oxide was grown on a silicon at different temperature? At temperature 350, silicon zinc oxide show a very poor crystalline quality, near about amorphous surface. But as the temperature is increased, the 002 peak is also increasing. Maybe higher temperature, these 002 peaks are related to the migration and diffusion of the atom at a high temperature. At a low temperature, they didn't get any specific place in the lattice. But as the temperature is increased, they found some specific place in the lattice, and that's why they sharp and intensive 00 peaks are shown at this temperature. The second thing, oxygen is mostly cases, in mostly papers, they use as a elimination of defect and impurity. But here, if we see that in this sample, these are all results we extracted through XRD. Full width, half maxima, grain size, dislocation density and texture. Here we will see the sample which is grown at a 500 degrees centigrade. They show a high stress. What's the reason? Reason, when they are grow at a high temperature, they decompose the metal organics and access zinc. But the other hand, at silicon is the oxidizing material and oxygen is always present at the zinc oxide film. So silicon captured the oxygen atom and there is a deficiency of oxygen, and this deficiency of oxygen affect the lattice parameter as well as stress. Therefore stress is increased as compared to other sample. What we will see in SEM figures. In SEM figures, there is at the sample which was grown at 350 degrees centigrade, a massive collisions of small grains. But as the temperature increased, these grains recombine each other and more systematics. But when the temperature more increase, these grains become originated and form such like a nano pillars. The one thing, sorry, I forgotten. There is a general rule, as I told you, with the increasing the temperature, the grain size should be increased. But here, they violate our rule. But in SEM figure, we believe that these X-rays diffractions are coming from the nanopillars. They are nanopillars, therefore the grain size becomes smaller. And the second reason, the film is so small as compared the other sample. What will be the in optical property? These are through PL measurement. They are measurement at a room temperature. Here we can see a short peaks. They are near band emission and also called the ultraviolet emission. Why these peaks are called near band edge emission. Sorry. These are called deep level emission and these are called near band edge emission. Near band edge emission is contributed to the exciton, while the deep level emissions are contributed to the impurity and defect, as I already told you. Here we got a result from through PL. If we see through the optical ratio, as the temperature is increased, intensity will also increase. The reason, temperature will increase with increasing the deposition time but decrease the non-radiative emission. And non-radiative emission is related to the deep level emission. And due to decrease of non-radiative emission, near band edge emission will increase. Here, the second sample. I already told you during the first sample, unintentionally we got a good result. Here you can see, unintentionally. But after the other sample, we make an idea, we got an idea. So we make a homoepitaxy template. Homoepitaxy, first zinc oxide with gallium doped 1% grow, then inhaled, then again grow on a zinc oxide. So that we want to get a more result. Here, first through AFM. After inhaling, we check the result. There is a small roughness. With the increasing the inhaling temperature, roughness also increase. The reason, due to the rapid growth of atom, you can see, they creates more roughness, and also grains diameter also increased. And these are results. After inhaling, then again grow the zinc oxide. Here you can see, inhaling, grain size increased at inhaling 9. The reason, the crystal dimensional become larger. Concentration of the point defect and impurity can be eliminated at higher inhaling temperature. And the film, here you can also see the texture coefficient also increased. Here all the sample through SEM figures, inhaling and then after growth zinc oxide, you can see. Actually our idea was that, after inhaling we will grow the zinc oxide again, then the grain size become bigger. Our idea was that, and they such like a nano pillars, but unfortunately we couldn't get such result. They become more suppressed, the grains, and you can see through the optical property. Here when the inhaling at 900 degrees centigrade, a sharp increase of deep level emission. I told you, deep level emission due to the impurity and defect. It means inhaling more effect on the optical property. Here, although a little bit change in full width half maximum, which was inhaled at 300, full width half maximum 15s, but inhaling they become a little bit small, not so much change. The third section, sample was grown by keeping oxygen rich or oxygen poor. Here you can see grain size almost same, no so much effect. The full width half maxima is approximately same, only difference. You can see these samples shows a polycrystalline nature, having a large peak. Here you can see also texture coefficient is greater due to the polycrystalline film. Here almost all peaks are same, a except having a large peak from the substrate. Maybe the film is so thin, not so much polycrystalline, they possess the short peak from the substrate. From SEM image, you can see a little bit, a small grain split up at a very large distance. They are almost different sample here. This sample oxygen is rich and this oxygen is low. So much effect on it. They have a high magnification and these are taken from the low magnification. To the optical property, you can see they change the optical property. In oxygen rich case, the intensity increase and the full width of maxima decrease in near band edge emission. But in deep level emission, it becomes opposite. It means we are not interested in deep level. Although deep level emission, they have much prospective property, but we are interested in near band edge emission. You can see not so much effect on it. These peaks, I'm sure that is from the sapphire, that is from the substrate. Here, zinc oxide on a silicon substrate. Second section I told you, we got an idea the sample has been grown on a homoepitaxy substrate, but didn't good result. In this time, zinc oxide was grown on a silicon substrate through heteroepitaxy. In this heteroepitaxy template, first silicon was cut by 8 degree, silicon carbide was cut by 8 degree, then again grow on a silicon through sublimation process. It is such like this plane. They are cutted by the 8 degree. Here you also can see from the AFM picture, and through SEM they show a hexagonal shape. Through structural property, they show the grain size increased, which the zinc oxide was grown on a p-type silicon carbide, and the zinc oxide doped with a gallium 1% on a p-type silicon carbide, grain size decrease. Maybe some affect gallium on it, but in the p-type the grain size, and here no other peaks were observed except 2 short peaks. And here, due to the miscut of 8 degree, we believe that each zinc atom sits at the same place of the silicon carbide, and that film is not polycrystalline, that is the epitaxy film. Because during XRD measurement, we also increase the incident angle by 8 degree, so that all the rays is incident on the same place. And they also, the texture coefficient will also increase, which the zinc oxide on a silicon. Through the SEM figures, you can see the zinc oxide doped with the gallium 1% show a poor microstructural quality. While the zinc oxide grown, N-type zinc oxide grown on a P-type, they show a very well established mono hexagonal shape are looking, and its diameter is 250 nanometer. And they can also prove through PI the sample which was doped on the gallium, as I show you here, they show a poor optical property. And the sample which was grown at p-type silicon carbide without doped it, they show a very sharp near band edge emission. So what will be the conclusion? Conclusion, the property of zinc oxide grown on a silicon at 500 degrees temperature, they show a very good optical property. The second thing, in attempt to use unintentionally made template by making oxide was grown on it, they didn't get more beneficial result for us. The third sample, the zinc oxide on a sapphire, shows some moderate influence on a optical property. For structural property, it didn't show any result. The zinc oxide, which was grown on a silicon carbide, through heterodeposition, they show a massive epitaxy relate zinc oxide hexagonal on a silicon carbide, you can observe. For the future work, I divided from two suggestions, from the experimental point of view and from the scientific challenges. From the experimental point of view, I observed the lowest size of the zinc oxide which was grown on a silicon, they show a nanopillars. And their density, if we increase the density and control the seed layer and higher and layer thickness, they can be useful for field emission property as well as show some good optical result. And from the determination of maximum possible time of growth, if we change the growth temperature, instead of 5, if we decrease the temperature, these nanopillars become more dense and they are good for the p-n junction or good morphology property. For the silicon carbide, as I told you, we used a p-type silicon carbide and grow on a n-type, and p and n, they form a p-n junction and they are used for a light emitting diode in the future. Thank you so much for your attention, and I really, from my supervisor, I appreciate they suggest me in every step and help me, especially for Voldemir. They've given me a good and beneficial suggestion in every step. Thank you very much. And all these groups for the material.
Okay, thank you very much. Now I can see that we have welcome all of you, but very busy people here. So maybe we change the procedure, if you don't mind.
Yes, it's good.
And if you have questions, let's start with questions first, and from the audience, and then we'll continue with the opponent examination. Yeah? Okay, so please, questions.
I have one question. You saw in the first set of sample you ground the silicon, and you saw 350, 400, 500, something like that.
Yeah.
And you indicate you see 500 give high optical quality.
Yeah.
But X-ray diffraction, so this very poor quality compared to.
Yeah.
And why like that?
Yeah, that's a very good question. Actually, in XRD, sample was placed parallel perpendicular to the incident ray. The incident ray, they are directly put on the nanopillars. They are not on the film. And through PL, the sample was parallel to the laser beam. And they show a very intensive peak of near band edge emission.
I still cannot tell. So you mean
So from nanopillar.
and X-ray diffraction?
Actually,
Okay. Yeah.
But maybe you can show the X-ray.
this one. Perhaps.
So here you say this you have a largest string in the when you grow 500.
Yeah.
If you grow nanopillar, they shouldn't have any string. I mean, the nanopillar will relax all the string.
But they are not in uniform pattern. They are
Okay.
a massive collision with each other. They are not in a uniform pattern. There is a cross-sectional view of SEM figure.
But I think actually the information is taken from the whole, not only from the nanopillars, also from the layer.
It must be. I mean,
Yes.
X-ray diffraction must be from the seeding layer.
Yes,
Then X-ray, then the photoluminescence maybe from nanopillar.
yes, from yes,
So that makes sense. Otherwise,
yes.
Can I add? Actually, we can say that at higher temperature of growth we have like bad quality of structural quality. If you will have a look more like carefully, in fact we have a summary signal from nanopillars and this seed layer. Moreover, this seed layer, can you show it as a picture? It has special planes. There is a special mechanism for formation of these nanopillars. So there is some signal, XRD signal from XRD spectra from these planes, and you can see. Can I have a look XRD spectra? Because you see it's like a triangle structure before nanopillars formation.
Slight faceting.
Yeah. So we strongly believe that these additional peaks that actually arise, 103 and 112, you see they are additionally, they are due to these tilted facets at the beginning of nanopillars. So that's, but if you have a look more attentionally on the 002 peak, it's still really narrow, and we believe that this one is from contribution from nanopillars by itself.
More questions? Okay, but maybe more questions will arise later, initiated by the questions of the opponent, so then we can proceed with the opponent.
First of all, I would like to say, and I could say it is very nice report, so many pages, very hard to read, with a lot of references. I could divide my work into two parts. I have some comments on the written part as well as I have some questions. First, I could start from questions. First, I have a question regarding this XRD spectrum. We can see one additional peak in case of 450. Second one peak, zinc oxide 101 peak. What does this mean?
This means the film shows a polycrystalline quality, having these two peaks with the increase in the temperature. And here you didn't see any peaks at 350 temperature. They show closely related to the amorphous. With increasing the temperature, the add atom become a specific place. They got a specific place, and they enhance these peaks of 002. 1002 peak.
Okay. Okay, if we see your report, at the end you wrote conclusions and general conclusions. But what does that mean? What is the difference between conclusions and general?
Actually, in this project, we divided in a 4 section. In the first section, the sample was grown on a silicon with rich oxygen. In the second section, zinc oxide was grown on a homoepitaxy template. And the third section, zinc oxide was grown on a sapphire by keeping rich oxygen or poor oxygen. And the fourth section, zinc oxide was grown on p-type silicon carbide. We divided 4 sections. In every section, I write at the end of simple conclusion, 2 or 3 lines, and after all, I write a general conclusion for all these samples.
So you could say that these are the overall conclusions
Overall
you draw from your entire work.
Yeah.
Even then these are conclusions. You could not say, I believe, because these are general conclusions. Okay, this is some general comment. I can't understand the motivation of the work. Okay. Few words more about motivation.
Motivation, I already told you, the first case, the zinc oxide was grown on a silicon because the zinc oxide on a silicon grow by direct method is a very difficult task because zinc oxide is an oxidizing material and easily captured the active oxygen, and they create the deficiency of oxygen is there. To grow the zinc oxide and the silicon, often people first grow a buffer layer, then grow again on a zinc oxide. But directly grow on a silicon was a very tough task, and this thing motivates, especially that's why sample was directly grown on a zinc oxide, and we want to check the result. This thing motivates us. In the second section, we make a homoepitaxy template, then again grow to the zinc oxide.
In which case? In case of silicon substrate.
In the first case, actually we want to check the result by direct growth of the zinc oxide on a silicon. And the second thing which motivates us, after getting a good result, we make a homoepitaxy template and then again grow the zinc oxide. And in the third section, the zinc oxide grown on a sapphire, we want to check by keeping oxygen rich or oxygen poor, what will be the effect on structural and optical property. And in the fourth case, N-type zinc oxide was grown on a P-type silicon. We want to check N and P on a silicon carbide. They have a close lattice mismatch. Their thermal and lattice mismatch is +5 and +1 respectively. How much close lattice mismatch, how much they affect on it. We want to check it.
Lattice mismatch between zinc oxide
And silicon
carbide. It is released in this case.
Yeah.
So you could believe that there is some sort of homoepitaxy.
Sorry?
You could believe that it is homoepitaxy.
Which type of
Between zinc oxide and silicon carbide.
Not homoepitaxy. But we got a good result
Okay.
due to the close lattice mismatch.
Okay. Then you calculate this 4 bits of maximum for 2 theta scans. Okay.
Yeah.
Does it have some relation with crystalline quality?
Yeah, of course, that is a correlate to the crystalline quality. Full width half maximum totally correlate with the crystalline quality.
In 2 theta case.
Yeah, in 2 theta case.
This is the 2 theta omega scan.
Yeah.
Or it is 2 theta
Yeah.
scan.
First, I will clear you, man. first you have a confusion. There is a no difference between omega and theta. Theta to 2 theta or omega to 2 theta scan.
Yes.
Here, actually, these are two, and before calculating the 2 theta, we have to find the value of psi, phi, omega, then we calculate the 2 theta value.
Okay.
And these 2 theta value gives us, and also the omega scan gives us the full width half maxima. How much? The small value of full width half maxima, it means they show a good crystalline quality. If the full width half maxima value is larger, wider, they show poor intensity, wide area, and wider peak of 002.
And it is made in a degree. Normally it is made in arc secant.
But most here the techniques we use, the oblique, they are given us the 2 theta value.
Obliques.
Oblique.
Okay. Yes, I have a few questions about the nanofillers. And you could assume that these are very nice for photoluminescent properties, good for this LEDs. How these are forming?
Not how they are forming. No one said they are intentionally. I said you that is unintentionally, and this thing motivates us. I already told. I want to make the homo epitaxy due to the motivation of nanopillars. Actually, maybe you didn't follow this thing. What I want, I already told you. Actually, therefore I make the homo epitaxy again on it, so that after the zinc oxide will grow on this part and they become a larger grain. They become a more larger nanopillars.
So you could say these pillars are sitting on the surface of the samples, not from the these are not starting from the substrate.
Sorry?
Ain't it?
Yeah.
I could say that this is your sample.
First of all, I will tell you. First of all, the thin layer form,
Okay.
then due to the nanopillars,
Okay.
the film become thin. But they
Okay.
are originated from the film,
Okay.
not from the substrate.
Okay. We have a substrate, then we have a very thin film of zinc oxide, and from that surface of the substrate they start.
Yeah.
Okay. It doesn't have any relation with
No.
latest mismatch or some stuff like that.
And here, can you explain how it's changed to the one-dimensional growth?
Sorry?
Higher
Actually,
temperature?
that thing, that was almost one-dimensional. And here we want more larger that become a two-dimensional or three-dimensional. But unfortunately, they become a one-dimensional. They correlated to the one.
And why it's changed to?
Sorry. Which thing?
Yeah, at 500 and higher temperature, you got this nano.
Yeah,
this,
nano.
Okay,
Yeah.
and then in others you didn't have.
Not.
Why it's happening? Why? How it's,
Yeah.
how they form or why they form?
Both things affect. Maybe due to the oxygen rich or high temperature effect on it. Both factor effects on it. Here you can see a totally different from these things. They are a hexagonal shape, but here they form a nanopillar tail. Here a very close, a massive grain, not so much randomly, but here the cross sectional view you can see they are randomly. But here,
So he mean to say that he has not investigated this behavior yet, that why it is forming, but it is forming with the increase in temperature.
Can I ask, if you don't mind? First of all, actually this result was unintentional for Sajjad probably, but we expected that. The point is, The point is that not only temperature is responsible for that growth, because you see the difference between 500 and 400, and another technological parameter has been changed. This is the zinc flow, and it means that the growth speed has been decreased. So we strongly believe that firstly, under high growth speed, we receive the thin film of these polycrystalline grains. Then, while decreasing the speed growth, we have received the growth. First of all, it was actually like the second stage of growth, or as I call it now, two-step growth process. So in this second step, we have actually homoepitaxy, and that is important. That is important because if you have a look more carefully, the size, the diameter of nanopillars is pretty small. It's around 35-40 nanometers, and it's really fine structure, especially for zinc oxide, like textured, because it's real nano size, and it is like you can see that it is located perpendicular to the substrate. That is really important. So, but this, we believe also that this can be obtained only via application this homoepitaxial growth. And why nanopillars? We believe that the growth in homoepitaxy at certain speed growth rate occurs due to so-called self-texture growth. Because hexagon of zinc oxide, hexagonal crystal, different planes has different free energy and atoms attachment energy, and thus different speed of growth. So it means that if you have a crystal, the fastest plane that will grow is the plane, basal plane, C plane, so-called. So if your crystal will grow like that, that is actually the results that we have for these pillars, because they are situated like hexagons, perpendicular to the substrate. But the resolution is too low even for SEM, so we can see the hexagons by itself.
So it means that the comparison should not be on the basis of the previous results, because if you are changing the rest of the parameters, so then that should be changed for the rest of the samples as well. So if you are presently working on this behavior, so then this should be explained just for this sample, that you have changed these parameters, and because of changing those parameters, your intention was to create this behavior, to form the nanopillars.
Can I answer?
Yeah.
I don't think that we said something about comparison. I'm the grower, so I decide what do I need, and the idea of Sajjad was to investigate. And this is a result of investigations. It gives to us information to explain about the growth technique and, growth process. That was main point. That was actually motivation for. Thanks.
No, this is actually different set of samples. So you are right, they cannot be compared with each other, but these are different sets. So grown on silicon under certain conditions, grown on sapphire under certain conditions, and grown on silicon carbide. And then it's the properties of course the main idea is to find the best conditions, to find the conditions which will give you the best material in terms of optical properties. Yeah.
So the consultation was on optical properties with respect to different substrates. Which substrate is supposed to give us good quality in terms of optical properties?
Well, not only substrate, because in each set of samples, the growth conditions will change. So that's why we don't compare. But still we can say that, this is a good optical quality material, which is there.
Okay. It was everything. Now I have very few comments on written part. If we see this report, it seems it's not just finalized because there is nothing abstract or acknowledgement, or chapters are not well defined. You don't know where the chapters are going to start. And if you see it critically, in some tables, tables are presented there, but there is nothing written what these papers are going to say, something like that. So I
Okay,
will
please
give
tell
this,
me at the last and nominate me. I will give. Tell
I will
me.
give you these, so
Okay.
you can have a look on your report. There are,
You should take into
Okay.
account all this. Yes.
so this was everything from me. Thank you very much.
Thank you. So, as an opponent, are you satisfied by what you
Yes,
say
it's
about
okay.
his work?
Yes, it's okay. It's nice work, very big report, lot of effort I could say. I read in 3 days.
Yeah, I think he has done a lot of work. So I hope that he has learned a lot of things from that. Yeah.
I have one question from you regarding the growth. Can you go to AP MOCVD picture? Okay, in the picture we could see that one board containing this
Zinc oxide
compound.
compound.
It is a compound, acetonate, zinc acetonate, something like that. How this precursor is going to deposit on substrate? How you are getting that precursor which is traveling toward, that is not so clear from here.
So, being honestly, it wasn't the main idea of this slide to make everything clear
Okay,
because it's technology.
okay.
Too confused.
You can't say anything.
I
And
You don't want to say it means.
I can explain. Of course, I won't do it. I
Okay,
mean that zinc acetylacetonate it's one of the metal organic precursors.
okay,
It looks like powder, like white
okay,
powder.
okay.
So it has been placed on the special heater.
Board, yes,
And then by controlling the temperature, and it actually melts like a snow and it vaporized. It's
Oh, okay.
sublimate, then it melts and vaporized again.
okay,
There is a certain vapor pressure. By tuning the temperature of heater,
okay,
you can control the flow actually of this precursor's vapor. And this
Okay.
precursor vapor contains zinc atoms inside.
okay,
Then by argon, with mixing of nitrogen, it depends on the experiment, we actually push it to the reaction
Okay.
zone, and there is oxygen already. So they are intermixing together and deposited on the
on the substrate. Okay.
Okay, are there any other questions? I think we have actually very good discussion, so please ask more questions.
So is it possible to go to zinc oxide and software in the result? I saw some shifting. Oh, yeah, back.
Yeah.
No, back. This is
No, that's
Here.
inhaling. Inhaling.
This was annealing.
This is so if you back that on that image.
Here is
No, no,
Oh,
no.
okay,
If you
yes,
go no back to that one here.
Actually, Reza was
Yeah.
pointing these peak are different, shifted a little bit.
Mm.
That are shifted to the inhaling at 900 degrees centigrade.
Okay.
Here they become a near band, deep level emission become higher. Why then they become smaller?
Mhm.
But do you know why it is shifted? I think this
Yeah,
is the
the
question.
question is why it's shifted.
That is, I'm not sure. And
This
this
is really-
thing also.
This is a nice question, and we would like to answer that. At present, we still don't know. But if it will be interesting for us, of course, we will.
And I am also curious to know
Maybe
that
due to different amount of stress in the material, you have different thermal expansion coefficients.
that's the general thing. Lattice mismatch, thermal
Yeah,
coefficient.
we have some suggestions, but we don't have at present.
Okay,
Yeah.
any good answer?
The other sample, they have also lattice mismatch and they have also stress, but they didn't show any result of there. And after inhaling, the atom should be recrystalline. They didn't show that peak.
I want to ask what impurities makes deep levels in samples?
Yeah, that is a divalent covalent zinc, oxygen vacancy, interstitious zinc.
Mm.
Such that.
Another technical question. You mentioned in XRD measurements that you get grain size, location density, and texture. From where you get these numbers? I mean, you calculate.
Oh, yeah.
But how?
Different publications.
What do you mean? I mean, you have to get them from your XRD peaks.
Yeah, XRD.
Just integrate it.
For texture from intensity.
From intensity.
Yeah,
Okay, so
from
all these
sample.
parameters.
So you have all these formulas and
Yeah,
expressions
yeah.
in the thesis.
Mhm.
If you want, I can send it.
There is a lot of.
Okay. Yeah. It's just interesting to see. Mhm.
Okay, more questions? No? Okay, then I think that here in this, on this paper, we have to, I have to consider the work of the student and the work of the opponent also. So I think both works were very good. So we put yes here. And if there's some other people who want to have this his names here, because I think it's important for the students to have been present at some thesis, but the thesis presentation. Please write down your name, your not any problem.
Something like integrate.
Okay, thank you for your.
Something
a little bit more RDS that you mentioned.